Made it out to Home Island again. It's been a real warm day today. It was drizzling earlier. You can see that there's a lot of water on the ice now. It can create bad spots if once the water starts drilling down through the ice will start opening up, developing holes, which is not good. Thought we'd see if we could see anything from here, but it looks like it's going to be awfully hazy because it's such a warm day. Even though it's nice and flat light, which would be ideal, there's just too much moisture in the air. Take a look at our target here. You can see that my tripod is still there, which I fully expected it to be. So I'm going to go up and mount the theodolite on the tripod and aim back at the barrel targets and see if I can make anything out. Well, we're up on the hill by the 6-mile target. The viewing is just totally lousy. I'll see if just barely can see out 3 miles. I have the Friends and Island channel marker focused in. It's just to the right of the vertical graticule. You can just barely make it out. It's just totally lousy. Not going to get anything done today. Well, keep our fingers crossed that we'll have something better come in the morning. Shoot the camera here. A lot of moisture in the air from that drizzle this morning. It's just lousy. Going to make some vertical angle measurements on the structure on Friends and Island. I have the graticule positioned at the base of the triangle of the channel marker. You can just kind of sort of see it there. And the vertical angle measurement is 90 degrees, 3 minutes and 15 seconds. Now I'm going to adjust it to the base of the supporting structure. There's some concrete bases there, so I'll be able to easily measure the distance with a carpenter's rule between the channel marker sign and that base. So now you can see I've got it positioned at 90 degrees, 6 minutes and 15 seconds. There you can see, oh, viewing's getting a little better. You can see it's at the base of the channel marker. So I'm going to go to Friends and Island and make that measurement. Loaded up, ready to hit towards Friends and Island. There's our trip odometer at 124.5. I'm not going to zero it out because I'm trying to keep track for gas mileage. So Friends and Island is out that way about a little over 3 miles. It's at 2.72 miles from the base station where the targets are, and we're about 6 miles out. So it's a little more than 3 miles. So head on out. Con gets a little nervous with all this. He doesn't like traveling on the ice this time of year in the vehicle. Plowing through a lot of water. Is coming up, less than a mile away. Start slowing down here. All right, at Franzen Island now. A lot of water on top of the ice. I'm gonna try to get a little closer here so I don't have to put my boots on. Yeah, this looks like a pretty good spot. All right, Con. Let's go. All right, Con. Get over here to measure some heights. Gotta be careful. The surface ice is really soft and slushy, could break through. Con's a good dog, he always leads the way. There. And there's the cement structures here that I measured, and then we're going to measure the distance from the top of those cement cubes on up to the bottom of the target. So now I'll get those measurements made. Let's see my estimate here. Oh gosh. Let's see, let's measure the rungs on the ladder and get an estimate. Okay, now I'm going to sight the ruler. I'm getting the tops lined up here. And it looks like the tops measure the 10.5 inches on the rule. And the rule is measured down from the 15th rung. Here the rungs, top to top, are exactly 1 foot apart. So going from where the rule is there, we'll count them. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and the 15th one right there. So, and now we'll measure the size of the blocks. Size of the blocks are 16 inches. For all practical purposes, 15 3/4 inches. So, that's our measurements. We'll go now and home and get this all figured out. See how close the angular measures match up with the actual lengths that I measured. I'm on top of the Franzen Island Lighthouse here. What a great view. Look back towards home Island. There's the 6-mile target. We're a little over 3 miles. That's the Canadian shore. Some reefs out in the water. And there's a paper mill at International Falls. Right there, but just so hazy. Just can't make anything out. That's my property right there. We might have a little bit of evening sun come out. A little break in the clouds there. Now that I made angular measurements with the theodolite, let's look at the angular measurement capability of my Topcon GTS 3C theodolite with its 5 arcsecond resolution. The resolution of the human eye is 0.02 degrees, or 1/50th of a degree, or 72 arcseconds. So the theodolite is 14.4 times better than the human eye. The human eye, again, has a resolution of 72 arcseconds. The theodolite is 5 arcseconds, which is 14.4 times better. And the other issue that we have is that the theodolite has crosshairs etched into its optics so that you can precisely align angular measure, whereas the human eye doesn't have anything like that. You have to basically guess, unless you have some reference points, you have to guess at what the angle is when you're getting down to the resolution of the eye. It's virtually impossible to guess what the angles are. Whereas with a theodolite, you can precisely measure those angles using the crosshairs etched into the optics. From Home Island, I sighted the channel marker on Franzen Island at time 2 minutes 59 seconds into the video here, and read the vertical angle at time 3 minutes and 15 seconds. And that vertical angle that I read on the Franzen Island marker was 90 degrees, 3 minutes and 15 seconds. I then aligned the theodolite to the top of the concrete blocks at the base of the structure at time 3 minutes 56 seconds into this video, and found that the vertical angle was 90 degrees, 6 minutes and 15 seconds. So what we had on Franzen Island that I was sighting, there's this channel marker structure. This is the bedrock, and to the sides there were 2 concrete blocks, or actually 4 around it. They're 16 inches high. And what I did on the first measurement from Home Island, I sighted to the base of the triangle of the marker and read the vertical angle as 90 degrees, 3 minutes and 15 seconds. Then I sighted it to the top of the concrete blocks, and I read the vertical angle there is 90 degrees, 6 minutes and 15 seconds. So the angular difference cited by the theodolite was exactly 3 minutes and 0 seconds. Well, 3 minutes in terms of degrees is you just divide minutes by 60, or 1/20th of a degree, or 0.05 degrees. Now, when we're trying to determine lengths, actual physical lengths through an angular measure, remember we have this relationship from perspective that if you're sighting a distance r out to a target whose length is d or height is d, the angular or the actual physical length of that object is d, then the relationship is that d equals the distance out, r, times the angular measure of that length in radians. It has to be expressed in radians, not degrees. So here I have degrees, and to convert this into radians, this is, say, our angle theta. So theta in radians is the degree measure. You divide by 180 and multiply by pi. Pi being 3.14159. So this angular measure of 5/100ths of a degree is 8.727 times 10 to the minus 4th radians. Now, the actual physical height I measured, remember by counting rungs on the ladder that was attached here, knowing that the rungs were 1 foot apart, and then looking at what I had left at the top and how much at the bottom, I found that we had 15 rungs. The rungs are 1 foot apart, so we have 15 rungs times 1 foot per rung. And then to that, I found on the 15th rung, the top of the blocks we're 10 1/2 inches below that rung. So we add to that 10 1/2 inches. But then up at the top, I found that the rung, the 15th rung, was a little bit above the top of the target bottom, which by about 3 1/2 inches. So we subtract off 3 1/2 inches. So we have 15 feet plus 7 inches. So this is, in decimal form, 15.58 feet. That is our D, the actual physical measurement of D over on Franzen Island. Now, let's compute the D from angular measure, knowing the distance from the theodolite to the channel marker, and compare the two. Now let's determine the distance between the theodolite and the marker on Franzen Island. The coordinates of the positions of the theodolite and the channel marker are as shown here. For the theodolite, it's 48.642817 degrees north by 93.186,579 degrees west. And for the marker, it is 48.627676 degrees north by 93.251551 degrees west. And these coordinates were determined both on Google Maps and verified in other videos that I've made related to this using my handheld GPS. So given those coordinates, the distance between the theodolite and the channel marker is 3.146 miles. And those are the positions. To the right is Home Island, where the theodolite was positioned, and to the left, lower left, is the channel marker at the point of Franzen Island. And that distance is 3.146 miles. Now, let's look at the distance, or the length between the bottom of the channel marker and the tops of those concrete blocks as determined by the theodolite. Again, what I cited with the theodolite was the bottom of the triangle of the channel marker and the tops of these concrete blocks. So I measured the angular measure between those two spots and physically measured it when I went to Franzen Island. Again, the physical measurement from the top of the block to the bottom of the target was 15.58 feet, and now we know that the angular measure is measured from the Home Island using the theodolite was exactly 3 arc minutes, which turns out to be 8.727 times 10 to the minus 4th radians. And given the coordinates of the theodolite and the Franzen Island channel marker, we know that the distance R between them is 3.146 miles. So now we can put it in. To determine this distance, this length, using theodolite, we take the distance, the sighting distance of 3.146 miles, and multiply it by the angular measure. Multiplying that out, we get 2.7455 times 10 to the minus 3rd miles, multiplied by 5,280 feet per miles to get this in feet. And this comes out to 14.50 feet. Now, the amount of uncertainty in this measurement with the theodolite, of course, is given by 5 arc seconds. That's the resolution uncertainty in the theodolite. So this theta in radians can vary by plus or minus 5 arc seconds. Well, at 3.146 miles, this works out to 5 arc seconds is 24.24 times 10 to the minus 6 radians. So we multiply this times the distance to get the uncertainty. So 24.24 times 10 to the minus 6 radians times 3.146 miles times 5,280 gives us the uncertainty in feet, and this comes out to 0.403 feet. So about a half a foot uncertainty over that distance. So this measurement here, then, determined by angular measure on the theodolite, is 14.5 plus minus 0.40 feet. So it could be 14.9 feet, or it could be 14.10 feet. Now let's compare. Well, the actual physical height length is 15.58 feet. So we've fallen short of that. Now why is that? Well, it was a very bad day. The viewing was terrible, terrible conditions. So what this is suggesting is there was considerable refraction, and comparing these two, we see that there's most likely image compression. The actual image is larger than what was measured using the optics of the theodolite. So most likely we had some compression. But this really isn't all that bad, and it's not surprising that, you know, we're out of the error bounds, but it still is really quite close between these two measurements. So it does show that we can use angular measure with a theodolite to determine the actual length of 2 points at a distance, if we know what the distance is, to the image that we're trying to determine the measure of, the physical measure of. So in coming days, I'm going to be using the marker on Franzen Island as viewed from my dock here on clear days. Now that I know precisely what the dimensions are on this particular target, I can confirm and try to verify the accuracy of the theodolite, which I will be doing. If you remember, here is each rung on the ladder is spaced by 1 foot. So between these cross members, there's 5 rungs. So these cross members are 5 feet apart. You've got 5 there, 5 there, 5 there, and another 5 down to here. And I know that the actual physical distance from the top of the blocks to the bottom of the target is 15.58 feet. I have some reference points to aim the theodolite towards, and I know precisely the different distance between my dock and the Franzen Island target. It's 2.72 miles plus a little bit, because the dock is about 50 feet, a little further west than the actual reference that I measured, that 2.72 miles last winter. So I just need to correct that, figure it out, get exactly the distance to the dock from that reference point that both myself and Jesse Kloslowski determined, and then I can get the actual feet probably well within a half a foot between the Franzen Island marker and the theodolite as it's mounted on my dock. And that's what I'll be doing. The next video that I'm going to be doing, the next update, we'll be talking a little bit more about my temperature measurement array using thermistors and how thermistors work, and lasers.
I have addressed lasers in a previous video last year. I believe it was in update 3 of my Rainy Lake survey. I refer you to go there to review, and I will add a little more to that about lasers because people have been commenting, why don't I use lasers? Well, I'm going to show you why I don't use lasers, because the theodolite and auto levels are much more precise than any laser in this particular application. Lasers have a lot of problems that you don't have with the theodolite. And to have a laser to give you the measurement capability that this theodolite does would require a laser to have beam collimation and beam expanders to collimate the beam well beyond the price range of any average person, and I'll be showing you that here in the next video.